So welcome to new class. We are starting with module 4, stiffness matrix method. So first definition is, what is stiffness? It is force required to produce unit displacement. So that can be explained using, consider a cantilever beam loaded at its free end with a point load. So that point load P will produce a deflection delta. Right, so as per the statement, stiffness is the force required to produce unit displacement. So when the delta becomes 1, force P will become stiffness K. It is represented by symbol K. So it is nothing but ഒരു യൂണിറ്റ് ഡിസ്പ്ലേസ്മെൻറ്റിന് കാരണമാവുന്ന ഫോഴ്സ് എന്തോ അതിനെ വിളിച്ച പേരാണെന്ത് സ്റ്റിഫ്നെസ്. ഓക്കെ, സ്റ്റിഫ്നെസ് ഈസ് ദി ഫോഴ്സ് ദാറ്റ് ഈസ് പ്രൊഡ്യൂസ്ഡ് ഡ്യൂ ടു യൂണിറ്റ് ഡിസ്പ്ലേസ്മെൻറ്റ്, or a force which produces unit displacement is called stiffness. Stiffness is an inherent property of the structure. Stiffness is force by displacement, and displacement will become delta equal to 1. Okay, this is the first definition. This is same for moment, that is moment required to produce unit rotation. Okay, instead of force we represented it as moment. Instead of displacement means translation, we represent it as rotation. So again, consider a cantilever beam loaded with its free end by a moment. ഫോഴ്സിന് പകരം മൊമെൻ്റ് ആണ് ഇവിടെ ലോഡ്. രണ്ടും ലോഡ് തന്നെയാണല്ലോ, വേറെ ഫോമിലുള്ള ലോഡാണ്. മൊമെൻ്റ് ഈസ് അനദർ ഫോം ഓഫ് ലോഡ് ഇറ്റ് സെൽഫ്. ആൻഡ് അപ്ലൈയിങ് എ മൊമെൻ്റ് എം, ഇറ്റ് വിൽ പ്രൊഡ്യൂസ് റൊട്ടേഷൻ, and that rotation is represented by symbol theta, that is slope. And when the slope will become equal to 1, the moment produced is called as stiffness. Okay, K is equal to m by theta. Now we are going to discuss stiffness matrix and stiffness influence coefficient, a 3-mark question. If there are n number of coordinates, that means coordinate means the point where load is applied. Okay, if there is 2 loads acting, that 2 load points may be the point where load is considered, or the node points, position where load is acting. We can say like that. Okay, so the stiffness matrix will be considered with respect to these coordinate points. Okay, so if there are n number of coordinates, and there will be n by n stiffness matrix will be there. And each term is called as stiffness influence coefficient. Each term in the stiffness matrix is called as stiffness influence coefficient. We represent it as Kij, where I stands for the position and J stands for the point at which displacement is applied. I stands for the position and J stands for the point at which displacement is applied, unit displacement is applied. So each term in stiffness matrix is called as stiffness influence coefficient. So Kij is force at coordinate I due to unit rotation at J. When I apply unit displacement at jth position, I get a force at ith position. In the similar way, I find all the stiffness influence coefficient for the whole structure. Now, a 3-mark question that can be asked is stiffness matrix method for a truss element. You have to derive truss element stiffness matrix. So, for example, we know this is a truss element. It has 3 elements and it is supported by roller and a hinge. So, consider one such element and then take that element as 2 joints, right? First joint and second joint. You apply a load P at any one joint. So this element 1-2 element is just experiencing a single load, that is P load, and that load causes the truss element to displace, and that displacement is represented by the letter delta. Delta displacement, axial force is applied and axial displacement delta occurs. We know by mechanics of solid we have studied delta is equal to PL by AE formula we have studied. Here by stiffness matrix method we studied that we will apply unit displacement, so delta will be 1. From that we will find out the value of P. P is equal to AE delta by L, where delta equal to 1. Therefore P is equal to AE by L is our answer for the stiffness matrix value. Here we just considered a single system coordinate. Hence, I obtained a single value of K. If I consider two system force coordinates, I would have got a 2 by 2 matrix. Okay. Next is derivation of a stiffness matrix for a beam element. Very important question, 3 mark question. So for a beam element, I am interested in considering a hinged support, that is a simply supported beam, two node points considered 1 and 2, and at that node point I am only interested in considering a rotation, that is rotation in clockwise direction, both clockwise direction rotation we assumed. And because we are assuming only that, because we are not interested in calculating translation. For beams, major force that occurs is a flexure. Okay, and we use the principle of superposition to analyze this beam and derive the equation for stiffness matrix. So case 1, apply unit displacement at the system coordinate 1. Our idea of a stiffness matrix is we are applying only unit displacement, right? Hence, we apply unit displacement at the first system coordinate point, considering the opposite node as fixed. That is our basic idea, because we are here, the stiffness matrix we are following is a elemental approach. In the elemental approach, we consider both the boundary conditions as initially fixed, and after which we apply the boundary condition. Here I am focusing on the first node point and then assuming the second node point as fixed. Okay, that's why I apply the unit displacement only at the first node point, that is a rotation, and the second end is assumed as fixed, and it will produce a rotation in the clockwise direction. And the yellow line indicates the displacement, how the beam displaces. It's a clockwise rotation, and the theta of clockwise is also positioned. That theta is actually the displacement. That theta is our slope, and the slope value is 1. So slope is equal to theta is equal to 1 we will get. Now we have to find the moment value at point 1 and point 2. So we are using slope deflection equation, that is point A and point B. We have to find the slope deflection equation and find the values of moment. That moment is nothing but the force, and that force is produced due to unit displacement. That is a unit slope, that is theta equal to 1, produces two moments, and that moment values are MAB and MBA. We are calculating MAB using slope deflection equation. MAB is equal to MFAB plus 2EI by L whole bracket 2 theta A plus theta B minus 3 delta by L. Since it's from A to B, we use 2 theta A plus theta B minus 3 delta by L. No sinking or support occurs since delta equal to 0. Also no applied forces. We are not applying any force, only moment is there. So fixed end moment is 0. So 2 EI by L, 2 theta A, the end theta A, there is a rotation, it will exist, and the value of slope is 1. So theta A is equal to 1. And theta B is equal to 0 since the end is fixed. Hence we will get 4 EI by L. That is my moment, fixed final end moment at end A, MAB, that is nothing but K11. What does K11 stand? First one stands for location, and second one stands for the point at which the unit displacement is applied. Here we are applying unit displacement at a first point itself. Hence second one is being used. Next we find MBA. Similarly, using slope deflection equation, MFBA plus 2 EI by L, 2 theta A plus theta, 2 theta B plus theta A minus 3 delta by L. Theta B is equal to 0 since it's a fixed end. Theta A is equal to 1, no sinking, delta 0. MFBA is equal to 0 since no external load. So you will get 2 EI by L into theta A, that is theta A is equal to 1. That is nothing but 2 EI by L, that is equal to MBA, that is equal to K21. Second position due to first load. Now apply unit displacement at a second node position and find out the force values at each node. Okay, that is K12 and K22. Now fixed end is A and load is applied or rotation is applied at a joint B, clockwise direction, produces a deflection clockwise direction, that is theta B equal to 1. Theta A is equal to 0 since it is a fixed end. And so the final end moments with A will be MAB 2 EI by L. Similar to the previous procedure, MBA will be 4EI by L, where MAB is equal to K12, low stiffness at a first point or force at first point due to displacement at second point. And K22 means displacement, force at second point due to displacement at a second point. That is 4EI by L. Adding up all the values, we will get a matrix of 4EI by L, 2EI by L, 2EI by L, and then 4EI by L. That is a 2 by 2 matrix. Okay, taking common 2EI by L outside, we will get 2EI by L into 2, 1, 1, 2.